Tonight, we're going to explore something that contradicts almost everything you think you know about stars. You've been told your entire life that stars are brilliant, blazing objects, balls of fire lighting up the cosmos, but here's what almost nobody realizes. Every single star that has ever existed, every star you've ever seen in the night sky, began its life in total darkness. Not dim light, not faint light, absolute darkness. A star is born inside a cloud so thick, so cold, and so black that no visible light escapes it. The object forming inside that cloud isn't even a real star yet. It's something else entirely. Something called a protostar. And what a protostar actually is, and how it slowly fights its way toward becoming a true star, is one of the most dramatic processes in the entire universe. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems obvious but is actually deeply misleading. When you think about stars, you think about light, you think about heat, you think about brilliant glowing objects burning across the darkness of space. And that makes sense because that's what stars are. Our sun, the star we know best, has a surface temperature of about 10,000 degrees Fahrenheit. Its core reaches 27 million degrees. It produces more energy every single second than all of human civilization has generated in its entire history. Stars are the brightest, hottest, most energetic objects in the visible universe, so it seems perfectly logical to assume that stars are born in bright, hot places, that they emerge from environments of intense energy and searing heat, that the birth of a star would be a spectacular visible event, an explosion of light and fire bursting into existence somewhere out in space. But that assumption is completely wrong. Not slightly wrong, not mostly wrong, completely, fundamentally, almost paradoxically wrong. Because stars are not born in light. They are born in darkness, not dim light, not faint, barely detectable light. Absolute, total, impenetrable darkness. The kind of darkness where visible light simply cannot exist. The kind of darkness where if you were somehow floating inside it, you would see nothing in any direction. No stars, no galaxies, no distant glow of any kind. Just black. Pure, cold, featureless black. Every star you have ever seen in the night sky, every point of light scattered across the darkness overhead, every sun orbiting at the center of every solar system in every galaxy across the entire observable universe. All of them began their existence in places so dark and so cold that they represent some of the most extreme environments anywhere in the cosmos. This is one of the great ironies of astrophysics. The objects that will eventually become the brightest things in the universe start out as the darkest. The things that will burn at millions of degrees begin at temperatures barely above absolute zero. The things that will shine for billions of years are born in places where light cannot penetrate. To understand how a star begins, you have to understand darkness first. So let's talk about where stars are actually born. They're born inside enormous structures called giant molecular clouds. These clouds are not like the clouds you see in Earth's sky. They're not made of water vapor drifting through an atmosphere. They're vast, sprawling regions of gas and dust, floating in the space between stars, inside galaxies like our Milky Way. And when I say vast, I mean genuinely, almost incomprehensibly vast. A single giant molecular cloud can stretch across dozens or even hundreds of light years. Remember that a single light year is about 5,880,000,000,000 miles. So a molecular cloud that's 100 light years across spans a distance so enormous that light itself, traveling at 186,000 miles per second, takes a full century to cross from one side to the other. These clouds contain enormous amounts of material. A single giant molecular cloud can contain enough gas and dust to make hundreds of thousands or even millions of stars like our sun. Some of the most massive molecular clouds contain material equivalent to 10 million times the mass of our sun. That's an almost inconceivable amount of matter gathered in one structure, The entire mass of our Sun, which is already 330,000 times the mass of Earth, multiplied by 10 million, all of it sitting in one region of space in the form of gas and tiny solid particles. But here's what makes these clouds so important for our story. They are extraordinarily cold. The gas inside a giant molecular cloud typically has a temperature of about 10 to 20 Kelvin. To put that in terms you might be more familiar with, that's roughly minus 440 to minus 420 degrees Fahrenheit. For comparison, the coldest temperature ever recorded on Earth's surface was about minus 128.6 degrees Fahrenheit, measured at Vostok Station in Antarctica in 1983. The interior of a molecular cloud is more than 300 degrees colder than that. These are temperatures so extreme that almost nothing moves. At these temperatures, atoms and molecules drift through space at a sluggish crawl compared to the frantic motion of particles in warmer environments. This extreme cold is not a coincidence. It's essential. It's one of the fundamental requirements for star formation. And to understand why, you need to understand what's actually inside these clouds. The gas in a molecular cloud is mostly molecular hydrogen. About 73% of the mass is hydrogen. About 25% is helium, and the remaining roughly 2% is everything else. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements in trace amounts. The hydrogen exists primarily in molecular form, meaning two hydrogen atoms bonded together into a single molecule. This is actually where the name molecular cloud comes from. In most of the space between stars, hydrogen exists as individual atoms or even as bare protons, stripped of their electrons by radiation and high temperatures. But inside these clouds, conditions are cool enough and dense enough for hydrogen atoms to pair up into molecules. This molecular hydrogen is important because it participates in the chemistry that allows other molecules to form, particularly carbon monoxide, which along with dust grains acts as an efficient radiator that helps the cloud shed heat and stay cold. But the gas isn't the only thing in these clouds. Mixed in with the gas are tiny solid particles called dust grains. These grains are incredibly small, typically only about 1/10 of a micrometer to 1 micrometer in size. That's roughly the size of particles in cigarette smoke. They're made of various materials including silicates, which are similar to the minerals in ordinary rocks, and carbonaceous compounds, which are complex molecules built around carbon atoms. Some dust grains are coated in thin layers of frozen water, carbon monoxide, carbon dioxide, methane, and ammonia. They're like microscopic icy pebbles floating through the gas. Dust makes up only about 1% of the total mass of a molecular cloud. 99% is gas, and only 1% is dust. That sounds insignificant. 1% seems like almost nothing, but that 1% changes everything, because dust is what makes these clouds dark. Dust grains are extraordinarily effective at blocking visible light. When photons of visible light encounter a dust grain, they're either absorbed by the grain or scattered off in a different direction. A single dust grain is tiny and insignificant. But when you have trillions upon trillions of dust grains spread across dozens of light years, the cumulative effect is devastating to any light trying to pass through. The dust absorbs and scatters so much light that the interior of a dense molecular cloud is completely opaque at visible wavelengths. No visible light from external stars can penetrate into the cloud's interior, and no visible light generated inside the cloud can escape outward. The cloud is, for all practical purposes, a wall of darkness. If you were standing outside the cloud looking at it against a background of stars, you would see a dark patch in the sky, a region where stars seem to disappear, a hole in the star field. This is exactly how astronomers first noticed these clouds. In the 18th and 19th centuries, astronomers observed dark patches and dark lanes in the Milky Way and wondered what they were. Some thought they were actual holes or gaps in the distribution of stars. The astronomer William Herschel, observing a dark region in the constellation Scorpius in 1784, famously remarked, that appeared to be a hole in the heavens. He thought there was literally nothing there. It wasn't until the early 20th century that astronomers like Edward Emerson Barnard realized these dark patches weren't empty space at all. They were clouds of gas and dust blocking the light of stars behind them. The darkness wasn't an absence of matter, it was a presence of matter. Dense, cold, opaque material sitting between us and the stars beyond. This is profoundly important for understanding star formation. Stars begin their lives inside these dark clouds. The very first stages of a star's existence happen in regions where no optical telescope can see. The birth of a star is a hidden event, concealed behind curtains of dust that block visible light, as effectively as a brick wall blocks your view of what's behind it. For centuries, humanity had no way to observe star formation directly because it happens in places that are invisible to our eyes and to the telescopes that detect the same kind of light our eyes detect. It wasn't until astronomers developed instruments sensitive to infrared light, radio waves, and submillimeter radiation, wavelengths that can penetrate dust, that we could finally peer inside these clouds and see what was happening. Dust blocks visible light, but it doesn't block everything. Longer wavelengths of light, particularly infrared and radio waves, can pass through dust much more easily. It's similar to how certain radio frequencies can pass through walls that block visible light. By observing molecular clouds at these longer wavelengths, astronomers revealed a hidden universe of activity inside what had appeared to be dark, empty voids. What they found was extraordinary. Inside these seemingly dead, dark, featureless clouds, stars were being born. Now, a giant molecular cloud isn't uniform. It's not a smooth, evenly distributed blob of gas and dust. Inside the cloud, the material is clumpy and structured. There are regions of higher density and regions of lower density. Filaments of denser gas thread through the cloud like veins through a body. And within these filaments, there are even denser concentrations of material. Astronomers call these dense cores, and they are the specific sites where individual stars or small groups of stars will eventually form. A dense core is typically a few tenths of a light year across, which translates to roughly several hundred times the distance from the Sun to Pluto. That might sound enormous, and by human standards it is, but compared to the overall size of the molecular cloud, which can be 100 light years or more, a dense core is tiny. It's a small knot within a vast structure. Inside a dense core, conditions are even more extreme than in the surrounding cloud. The temperature drops to as low as 6 to 10 Kelvin, which is roughly minus 448 to minus 440 degrees Fahrenheit. The density of gas, while still incredibly low by any earthly standard, is much higher than in the rest of the cloud. In a typical dense core, there might be about 10,000 to 1 million molecules per cubic centimeter. That sounds like a lot, but for comparison, the air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. That's 25 followed by 18 zeros. Even the densest molecular cloud core is a better vacuum than anything we can create in laboratories on Earth. Yet, by the standards of interstellar space, where there might be only one atom per cubic centimeter, a dense core is remarkably crowded. These dense cores are also extremely dark. The dust within them is so concentrated that even infrared light has difficulty penetrating to the very center. The deep interior of a dense core is one of the darkest, coldest, most isolated places in the entire galaxy. No starlight reaches it. No warmth from any external source penetrates it. It exists in a state of profound cold and darkness, cut off from the rest of the universe by layers of obscuring dust. And yet, this is where a star will be born. This frozen, lightless knot of gas and dust is the cradle of a future sun. But a dense core doesn't automatically collapse to form a star. There's a battle happening inside it, a tug of war between forces that want to pull the core together and forces that want to keep it spread out. On one side is gravity. Every particle of matter in the core exerts a gravitational pull on every other particle. Gravity wants to pull all the material inward, to collapse the core into a smaller, denser object. On the other side are several forces resisting this collapse. The most important is thermal pressure. Even at temperatures of only 10 Kelvin, the gas particles are still moving. They're moving very slowly compared to gas at room temperature, but they're still moving. This motion creates an outward pressure that resists gravitational collapse. Think of it like trying to squeeze a balloon. The air inside pushes back against your hands. The gas inside a dense core pushes back against gravity in a similar way. There's also turbulence. Gas inside molecular clouds isn't perfectly still. It's constantly stirring, swirling and churning in complex patterns driven by various energy sources. This turbulent motion creates additional pressure that helps support the cloud against collapse. And in some cases, magnetic fields also play a role. Molecular clouds are threaded with magnetic field lines, and charged particles in the gas interact with these fields. This magnetic pressure can provide additional support against gravitational collapse, acting almost like an invisible scaffolding that helps hold the cloud up. So the dense core sits there, suspended in a delicate balance, gravity pulling inward, thermal pressure, turbulence, and magnetic fields pushing outward. For a long time, possibly millions of years, this balance can hold. The core sits in the cold darkness, stable, unchanging, waiting. But this balance is fragile. It doesn't take much to tip it, and the universe provides plenty of ways to tip it. One of the most common triggers is a shock wave from a nearby supernova. When a massive star explodes at the end of its life, it sends a blast wave rippling outward through the surrounding space at thousands of kilometers per second. When this shock wave slams into a molecular cloud, it compresses the gas. Regions that were barely stable suddenly find themselves squeezed to higher densities. The additional compression increases the gravitational pull within those regions, and if the compression is strong enough, gravity overwhelms the outward forces, and collapse begins. There's something poetically beautiful about this. A dying star, in its final violent explosion, sends out a shock wave that triggers the birth of new stars. Death and birth linked across the darkness of space. The atoms scattered by the explosion of one star eventually become the raw material for new stars and new planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, much of it was forged inside massive stars that exploded billions of years ago, sending shockwaves through molecular clouds that triggered the formation of new generations of stars, including our sun. But supernovas aren't the only trigger. The collision of two molecular clouds can compress gas enough to initiate collapse. The spiral arms of a galaxy can act as density waves, regions of higher gravitational potential that sweep through the disk of the galaxy. As a molecular cloud passes through a spiral arm, the increased gravitational compression can trigger star formation. Winds from massive young stars already forming nearby can compress neighboring gas. Even the gravitational influence of nearby star clusters can nudge a dense core over the edge from stability into collapse. There's a critical concept here that astronomers use to describe when collapse becomes inevitable. It's called the Jeans instability, named after the British physicist Sir James Jeans, who worked out the mathematics in the early 1900s. The basic idea is straightforward. For any given cloud of gas at a particular temperature and density, there's a critical mass above which gravity will overcome thermal pressure and collapse will begin. This critical mass is called the Jeans mass. If a dense core has a mass greater than its Jeans mass, it will collapse. If it has a mass less than its Jeans mass, thermal pressure will hold it up and it will remain stable. The Jeans mass depends on two main factors: temperature and density. Higher temperatures mean faster moving gas particles, which means more outward pressure, which means you need more mass for gravity to win. Higher densities mean stronger gravity, which means you need less total mass for collapse to begin. This is precisely why the extreme cold of molecular clouds matters so much. Because the gas is so cold, the thermal pressure resisting gravity is very low. The particles are moving sluggishly, they're barely pushing outward at all, This means the gene's mass is low. It doesn't take as much material for gravity to overcome the resistance and trigger collapse. If the gas were warm, say room temperature, the gene's mass would be enormously higher. You'd need far more material concentrated in one place for gravity to win. Star formation would be far less common, or might not happen at all in many regions. The extreme cold of molecular clouds is what makes star formation possible. It reduces the threshold for gravitational collapse, allowing relatively modest concentrations of gas to begin the process of forming a star. The darkness and the cold aren't obstacles to star formation, they're prerequisites. Without the cold, the gas couldn't collapse. Without the dust creating that cold, dark environment, the gas would be heated by starlight and unable to reach the low temperatures needed for collapse. The darkness isn't just where stars happen to be born, the darkness is why they can be born at all. So picture this moment. A dense core sits deep inside a giant molecular cloud. It's been sitting there for perhaps 1 million years, cold and dark and quiet. The temperature is about 10 Kelvin. The gas is mostly molecular hydrogen with a sprinkling of helium and trace amounts of heavier elements. Dust grains drift through the gas, tiny frozen particles smaller than the wavelength of visible light. No starlight penetrates this deep. The core exists in absolute darkness. Then something changes. Maybe a shock wave from a distant supernova reaches the cloud and compresses the core slightly. Maybe the cloud drifts through a spiral arm and the increased density tips the balance. Maybe turbulence within the cloud itself creates a momentary compression that pushes the core past its gene's mass. Whatever the trigger, the result is the same. Gravity gains the upper hand. The outward forces can no longer hold the core up, and the core begins to collapse. This is the moment. This is where everything begins. Not with an explosion, not with a flash of light, not with any visible event at all. The core begins to fall inward under its own gravity, silently, invisibly, in perfect darkness. No telescope on Earth could see it happening in visible light, because the event is buried behind layers of opaque dust. No human eye could witness it because it happens in a place where visible photons simply do not exist. The birth of a star begins as one of the most quiet, hidden events in the universe. Matter slowly, inexorably, falling inward in the dark. There is no drama visible to the naked eye, no cosmic fireworks, just cold gas responding to the most fundamental force in the universe. Gravity. The same force that holds you to the ground, that keeps the moon in orbit around Earth, that keeps Earth in orbit around the sun. In this dark, frozen corner of the galaxy, gravity begins the long, slow process of building a star from nothing but gas and dust. And here's what's remarkable. This process is happening all the time. Right now, at this very moment, in molecular clouds scattered across the Milky Way, dense cores are collapsing. Future stars are beginning their lives in absolute darkness. Some of them will become massive blue giants that will burn through their fuel in a few million years and explode as supernovae. Others will become modest yellow stars like our sun, burning steadily for 10 billion years, perhaps warming planets where life takes hold. Others still will become tiny red dwarfs, barely large enough to sustain nuclear fusion, burning so slowly and so faintly that they'll still be shining trillions of years from now, long after our sun has died and faded to a cold, dark cinder. But right now, all of them begin the same way, as collapsing knots of gas in the cold, dark interiors of molecular clouds. The universe's most brilliant objects starting their existence in its darkest places. The Milky Way alone forms roughly 1 to 3 new solar masses worth of stars every year. That might not sound like much, but it means that somewhere in our galaxy, right now, a dense core is crossing the threshold, matter is beginning to fall, a protostar is about to be born, and nobody can see it. Not yet, because it's still hidden, still buried in dust, still wrapped in darkness. The light will come later. First, there is only the fall. The collapse of a dense core is not a fast event by human standards. It unfolds over tens of thousands to hundreds of thousands of years, depending on the mass and density of the core. From our perspective, nothing seems to be happening. If you could somehow watch the core, even with instruments that can see through dust, the changes would be imperceptible from day to day, from year to year. But gravity is patient. It doesn't need to rush. It just needs to keep pulling, steadily, relentlessly, drawing matter inward, compressing it, concentrating it. And as the matter falls inward, something begins to change. Something that will eventually transform this cold, dark knot of gas into a hot, glowing object. The falling material begins to heat up, not from any external source, not from nuclear reactions, not from starlight or radiation. It heats up simply because it's being compressed. This is where the story of the protostar truly begins. In the next stage of this journey, we're going to follow that collapsing core as it falls inward, watch it heat up, and see the first faint glow of a protostar emerge from the darkness. Because what happens next, the physics of how gravity turns cold gas into a blazing hot object without any nuclear fusion at all, is one of the most beautiful and counterintuitive processes in all of nature. So the dense core has begun to collapse. Gravity has won the battle against thermal pressure, turbulence, and magnetic fields. Matter is falling inward. But what does that actually mean in physical terms? What does it look like? What does it feel like? What actually happens when a cloud of gas that's dozens of times larger than our entire solar system starts falling in on itself? Let's slow this process down and walk through it carefully, because this is where the physics becomes truly extraordinary. When the collapse begins, the dense core is enormous. It might be 1/10 of a light year across, or even larger. That's roughly 600 billion miles. For comparison, the distance from the Sun to Pluto is only about 3,700,000,000 miles. This collapsing core is hundreds of times larger than the entire orbit of Pluto, and the material inside it is incredibly spread out. Even though it's the densest part of the molecular cloud, the gas is still far thinner than the best vacuum we can create in any laboratory on Earth. There are maybe a few tens of thousands of molecules per cubic centimeter. If you could somehow scoop up a cubic meter of this material, it would weigh less than 1/1000,000,000 of a gram. This is not dense by any standard we would recognize in our everyday lives. It's almost nothing. But across the vast volume of the core, all those almost nothings add up. The total mass of the core might be 1 or 2 times the mass of our Sun, or it might be several times the mass of our Sun, depending on the core. And all of that mass is now falling inward, accelerating under the pull of its own gravity. In the earlier stages, this collapse is essentially free fall. Free fall means the material is falling inward under gravity with nothing significant opposing it. The thermal pressure that was previously holding the core up has been overcome. The gas is so cold and so thin that as it compresses, the heat generated can still be radiated away efficiently. Molecules of carbon monoxide and dust grains act as tiny radiators, absorbing the energy produced by the mild compression and re-emitting it as infrared and submillimeter radiation that escapes the cloud. Because this heat can escape, the pressure inside the core doesn't build up significantly during the early stages. Gravity just keeps pulling, and the material just keeps falling. This phase of the collapse is sometimes called isothermal collapse, because the temperature remains roughly constant even as the density increases. The gas is falling faster and faster, getting denser and denser, but staying at roughly the same frigid temperature because it can radiate away the heat of compression as quickly as it's generated. Think about what this means physically. Imagine an enormous region of space, hundreds of billions of miles across, with gas slowly drifting inward from every direction. At first, the motion is almost imperceptible. The gas molecules are drifting inward at fractions of a kilometer per second. But gravity is relentless. It accelerates the gas continuously. The farther the gas falls, the faster it goes. And as the material converges toward the center, the density increases. More mass concentrated in a smaller volume means stronger gravitational pull, which means faster infall, which means even more rapid compression. It's a runaway process, a gravitational avalanche in slow motion. Slow by human perception anyway. The free fall time for a typical dense core is somewhere between 50,000 and a few 100,000 years. That might sound long, but in astronomical terms, it's remarkably fast. Stars live for millions or billions of years. The collapse that creates them happens in a comparative blink. Now, here's where something critical changes. As the center of the core gets denser and denser, a point is reached where the gas can no longer radiate away heat as fast as it's being generated. The density becomes high enough that the gas starts to become opaque to its own infrared radiation. The photons that were previously carrying heat away start getting trapped. They bounce around inside the dense gas, absorbed and re-emitted over and over, unable to escape. This is a fundamental transition. Before this point, the collapsing gas could cool itself efficiently. The collapse was isothermal. The temperature stayed roughly constant. But now, with the heat trapped inside, the temperature begins to rise. And as the temperature rises, so does the thermal pressure. The gas starts pushing back against gravity again. This doesn't happen all at once throughout the core. It happens first at the very center, where the density is highest. The outer regions of the core are still in free fall, still collapsing freely, still cold. But at the center, a small region has become dense enough and opaque enough that heat is building up. The temperature at the center starts climbing. From 10 Kelvin, it rises to 20, then 50, then 100, then several hundred Kelvin. The thermal pressure builds and builds until it reaches a point where it's strong enough to halt the collapse at the center. The inward pull of gravity is now balanced by the outward push of thermal pressure. The center of the collapsing core reaches what physicists call hydrostatic equilibrium. Gravity pulling in equals pressure pushing out. The collapse stops, at least at the center. This is the formation of what astronomers call the first hydrostatic core. It's a small, dense, warm object sitting at the center of the still collapsing cloud. It's not very large. Typically, it's only about 5 to 10 astronomical units across. An astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So this first core is roughly 5 to 10 times the diameter of Earth's orbit around the Sun. That might sound big, but remember that the original dense core was hundreds of billions of miles across. This first hydrostatic core is tiny in comparison. It's the first concentrated object to form from the collapse, the first seed of the future star, and it's warm. Not hot by stellar standards, not even close, but warm compared to the freezing cloud around it. Its temperature might be a few hundred to about 2000 Kelvin at this stage. But there's something important to understand about this first core. It's not stable. It can't last. Because while the center has temporarily halted its collapse, the outer regions of the cloud are still falling inward. Material is still raining down on the first core from all directions, adding mass and energy. And something else is happening inside the core that will soon destroy this temporary equilibrium. At temperatures around 2000 Kelvin, a critical chemical event begins. The molecular hydrogen that makes up most of the gas starts to dissociate. Molecular hydrogen, remember, consists of two hydrogen atoms bonded together. At low temperatures, this bond is stable. But at around 2000 Kelvin, the molecules have enough thermal energy to break apart. Each molecule of hydrogen splits into two individual hydrogen atoms. This process, called dissociation, requires energy. Quite a lot of energy, actually. Breaking the bond between two hydrogen atoms absorbs energy from the surrounding gas. This is energy that was previously contributing to the thermal pressure holding the core up against gravity. As the hydrogen dissociates, it essentially sucks energy out of the gas. The temperature stops rising even as the core continues to be compressed. The pressure support falters. Think about what's happening at the molecular level inside this small, warm object. Every molecule of hydrogen is vibrating, rotating, bouncing off its neighbors. The temperature has climbed high enough that these collisions are becoming violent. Two hydrogen atoms that have been bonded together for perhaps millions of years, drifting peacefully through the cold, dark cloud, are now being shaken apart by the thermal energy around them. Each time a molecule splits, it absorbs a specific amount of energy from the surrounding gas. Multiply this by the trillions upon trillions of molecules dissociating throughout the core, and the total energy drain is enormous. The gas is being compressed, which should heat it up. But the energy that would normally raise the temperature is instead being consumed by the dissociation process, ripped away molecule by molecule. It's as if you were trying to heat a pot of water, but every time the temperature started to rise, something invisible reached in and pulled the heat away. The core is caught in a trap. Gravity is squeezing it harder and harder, but the dissociation of hydrogen is stealing the thermal energy that should be fighting back. The pressure support weakens, and then it fails, and then gravity wins again. Without sufficient thermal pressure to hold it up, the first hydrostatic core undergoes a second collapse. This second collapse is dramatic and fast. The core falls inward again, much more rapidly than the first collapse. The density skyrockets. The temperature surges as the dissociation of hydrogen is completed, and the compression energy can once again heat the gas. Within a very short time, astronomically speaking, the center of the collapsing region reaches temperatures of tens of thousands of Kelvin. The hydrogen atoms themselves begin to ionize, their electrons being stripped away by the intense thermal energy. The gas becomes a plasma, a state of matter where atoms are broken into their component parts, bare nuclei and free electrons. And then, once again, the collapse halts. The temperature and pressure at the center become high enough to establish a new hydrostatic equilibrium. This time, the object that forms is much smaller and much hotter than the first hydrostatic core. It might be only a few solar radii across. A solar radius is about 432,000 miles. So this object is roughly a few million miles in diameter, about the size of our sun or a few times larger. But its mass at this point is tiny. It might contain only about 1% of the total mass that will eventually make up the finished star. The rest of the material is still in the surrounding envelope, still falling inward, still raining down onto this newborn object. This is the protostellar core. This is the protostar. This is the moment when we can point to a distinct, coherent, self-gravitating object and say, there it is. That's going to become a star. But it's crucial to understand what this object is and what it is not, because a protostar is not a star. Not yet, not even close. A true star, a main sequence star like our sun, is powered by nuclear fusion. Deep in the core of a main sequence star, hydrogen nuclei are being slammed together with such force that they fuse into helium nuclei. This fusion process releases enormous amounts of energy that flows outward through the star and eventually radiates into space as the light and heat we observe. Nuclear fusion is what makes a star a star. It's the defining characteristic. It's what allows a star to shine steadily for millions or billions of years without collapsing or expanding. The energy from fusion creates the outward pressure that perfectly balances gravity, maintaining the star in a stable equilibrium. A protostar is not doing this. At the moment of its formation, the protostellar core is far too cool for hydrogen fusion. The core temperature might be tens of thousands of Kelvin. That's hot by everyday standards, certainly hot enough to vaporize any solid or liquid material, but hydrogen fusion requires temperatures of roughly 10 million Kelvin. The protostar isn't even close to that threshold. It's off by a factor of hundreds. So where is the protostar's energy coming from? Why is it hot? Why does it glow? The answer is gravity. The protostar is heated entirely by the energy of gravitational collapse. This might sound strange, so let me explain it carefully because it's one of the most important concepts in all of stellar physics. When matter falls inward under gravity, it accelerates. It gains speed, and moving matter has kinetic energy, the energy of motion. When this fast-moving material slams into the surface of the forming protostar, or when the protostar itself contracts under its own weight, that kinetic energy is converted into thermal energy. Heat. The gas heats up not because anything is burning, not because any chemical or nuclear reaction is occurring, but simply because gravitational potential energy is being converted into thermal energy through compression and impact. This is actually a very familiar concept if you think about it the right way. When you pump air into a bicycle tire with a hand pump, the pump gets warm, not because anything is burning inside it, but because you're compressing air. The act of compression itself generates heat. The molecules of air get squeezed into a smaller space, they collide more frequently and more energetically, and the temperature rises. The same basic principle is at work in a collapsing protostar, just on an incomparably larger scale. Trillions upon trillions of tons of gas falling inward, being compressed by the relentless force of gravity, converting gravitational potential energy into heat. The deeper the gas falls, the more energy it releases. And because a protostar is massive, the gravitational potential energy involved is enormous. There's actually a well-known result in physics called the Kelvin-Helmholtz mechanism, named after Lord Kelvin and Hermann von Helmholtz, two 19th century physicists who studied this process. Before nuclear fusion was understood, Kelvin and Helmholtz proposed that the sun's energy came entirely from gravitational contraction. They calculated how long the sun could shine by slowly shrinking and converting gravitational energy into heat. Their answer was about 20 to 30 million years. That turned out to be far too short. The sun is about 4.6 billion years old, and nuclear fusion is what has kept it burning for all that time. But Kelvin and Helmholtz weren't wrong about the physics. Gravitational contraction does produce heat. It's just not enough to power a star for billions of years. For a protostar, however, gravitational heating is everything. It's the only energy source the protostar has, and it's enough to make the protostar genuinely hot and genuinely luminous. At this early stage, the protostar is actually quite luminous. Not because it's efficient at producing light, but because it's large and it has a lot of gravitational energy to release. A protostar can be several times more luminous than our sun, even though it's not fusing any hydrogen at all. All of that luminosity comes from gravity, from matter falling onto the protostar's surface, from the protostar itself slowly contracting and heating up, from the conversion of potential energy into radiation. This is one of the most counterintuitive things about protostars. They can actually be brighter than many Finnish stars, at least temporarily, powered entirely by gravitational energy rather than nuclear fusion. But here's the thing, you can't see any of it. Not with your eyes, not with any optical telescope, because the protostar is still buried deep inside its natal envelope. All that gas and dust that made up the original dense core hasn't gone away. Most of it is still there, surrounding the protostar, still falling inward. The protostar sits at the center of this cocoon, like a glowing ember buried inside a mountain of ash. The visible light that the protostar emits is immediately absorbed by the surrounding dust. It never makes it out. The dust absorbs the short wavelength visible and ultraviolet light, and re-emits the energy at much longer wavelengths, primarily in the far infrared and submillimeter. So while the protostar is hidden at visible wavelengths, it can be detected at infrared wavelengths. The dust-shrouded cocoon glows warmly in the infrared, heated by the protostar within. From the outside, at visible wavelengths, there's nothing to see. Just darkness. The same cold, dark, opaque cloud that was there before. But at infrared wavelengths, there's a warm spot glowing softly in the heart of the cloud. That warm spot is the signature of a newborn protostar. This is what makes the study of protostars so challenging. You can't just point a regular telescope at the sky and see them. You need specialized instruments that detect infrared radiation or radio waves. For most of human history, we had no such instruments. We could see the finished stars, we could see the dark clouds, but we couldn't see what was happening inside the clouds. The connection between darkness and starlight was invisible to us. It was like watching caterpillars and watching butterflies, but never being able to see the cocoon. We knew the transformation happened, but the actual process was hidden. This began to change in the second half of the 20th century. Astronomers developed detectors sensitive to infrared radiation. Early infrared observations in the 1960s and 70s were crude by modern standards, limited by Earth's atmosphere, which absorbs most infrared wavelengths before they reach the ground. But even those early observations revealed tantalizing hints of warm objects hidden inside dark clouds. There were infrared sources with no visible counterparts, glowing warmly at wavelengths the eye could not see, sitting in exactly the places where theory predicted protostars should be forming. These detections were revolutionary. For the first time, astronomers weren't just theorizing about what happens inside molecular clouds. They were seeing it, dimly and imprecisely, but seeing it nonetheless. The real breakthroughs came with space-based telescopes that could observe above Earth's atmosphere. The Spitzer Space Telescope, launched in 2003, was one of the first space-based observatories capable of surveying large areas of the sky in infrared light. It revealed thousands of protostars hidden inside molecular clouds that had previously appeared as nothing but dark voids. Spitzer could detect the warm glow of protostars still deeply embedded in their envelopes, objects so young and so obscured that no optical telescope had ever seen them. Entire nurseries of forming stars were revealed for the first time. Hundreds of protostars clustered together inside a single molecular cloud, each one at a different stage of formation, each one slowly emerging from its dusty cocoon. The Herschel Space Observatory, launched in 2009, observed at even longer wavelengths in the far infrared and submillimeter, detecting the coldest and most deeply embedded protostars. Herschel was particularly important because it could see the very youngest protostars, the class 0 objects that are so deeply buried that even mid-infrared radiation can barely escape. These are protostars in the first few tens of thousands of years of their existence, still almost completely hidden, still wrapped in massive envelopes of gas and dust. Before Herschel, these objects were almost impossible to study. After Herschel, astronomers had catalogues of them, hundreds of newborn protostars mapped across the Milky Way, and the Atacama Large Millimeter-Submillimeter Array, known as ALMA, a collection of 66 radio telescopes in the high desert of Chile, has given us unprecedentedly detailed images of protostellar systems, revealing not just the protostars themselves, but the structures of gas and dust surrounding them with extraordinary clarity. ALMA operates at millimeter and submillimeter wavelengths, which penetrate dust even more effectively than infrared light. It can resolve structures within protostellar systems at scales of just a few astronomical units, revealing the accretion disks, the outflow cavities, and the density structures in the envelopes with a level of detail that would have been unimaginable just a few decades ago. Without these tools, protostars would be completely invisible to us. We would know that molecular clouds exist because we could see the dark patches they create. We would know that stars exist because we can see them shining in the sky. But the connection between the two, the process by which dark clouds give birth to shining stars, would remain entirely hidden. It's only because we developed the technology to see through dust using wavelengths of light that dust cannot block that we've been able to piece together this story. Now, let's talk about what the protostar looks like at this stage in more detail. The protostellar core sits at the center of a large envelope of gas and dust that's still in falling. This envelope might extend outward for thousands of astronomical units. Material from the envelope is falling inward continuously, raining down on the protostar and adding to its mass. The protostar at this point might have only a fraction of its final mass. Most of the material that will eventually make up the finished star is still in the envelope, still on its way down. The rate at which material is falling onto the protostar is called the mass accretion rate. In the earlier stages, this rate can be quite high, perhaps a few hundred thousandths of a solar mass per year. That might not sound like much, but sustained over tens of thousands of years, it adds up quickly. As material falls onto the protostar, it hits the surface at very high speeds. Depending on the mass of the protostar and the distance the material has fallen, impact velocities can reach tens or even hundreds of kilometers per second. When gas moving at these speeds suddenly decelerates upon hitting the protostar's surface, the kinetic energy is converted into heat. This creates an extremely hot boundary layer on the protostar's surface, a region where temperatures can reach millions of degrees locally. This accretion shock, as it's called, is one of the primary sources of the protostar's luminosity during this early phase. The energy released by accretion doesn't just heat the protostar, it also heats the surrounding envelope. The inner regions of the envelope, closest to the protostar, are warmed to temperatures of hundreds or thousands of Kelvin. Farther out, the envelope remains cold, still close to its original temperature of 10 to 20 Kelvin. This creates a temperature gradient in the envelope. Hot near the center, cold at the edges. The dust in the inner envelope absorbs the protostar's radiation and re-emits it at infrared wavelengths. Dust farther out, which is cooler, re-emits at even longer wavelengths in the far infrared and sub-millimeter. This layered structure of temperatures and emission wavelengths is one of the ways astronomers can study protostars. By observing at different wavelengths, they can probe different layers of the envelope, building up a picture of the conditions at various distances from the central protostar. One thing that needs to be absolutely clear at this stage is what the protostar is not doing. It is not fusing hydrogen. There might be some minor nuclear reactions happening. Deuterium, a heavy isotope of hydrogen that contains one proton and one neutron, can fuse at temperatures lower than those required for regular hydrogen fusion. Deuterium fusion begins at roughly 1 million Kelvin, which many protostars do reach at some point during their contraction. But deuterium is extremely rare. It makes up only about 0.002% of all hydrogen. Deuterium fusion produces some energy, but nowhere near enough to halt the protostar's contraction or to serve as a long-term energy source. It's a brief footnote in the protostar's evolution, not a defining feature. The protostar burns through its small supply of deuterium relatively quickly, and then continues contracting. The defining energy source of a protostar remains gravity. Gravitational contraction and the energy released by infalling material are what keep the protostar hot and luminous. This is the fundamental distinction between a protostar and a true star. A true star is in equilibrium. Nuclear fusion in its core produces energy that balances gravity, and the star can maintain this balance for millions or billions of years. A protostar is not in equilibrium in the same way. It's still contracting, still accreting, still evolving. Its energy comes from gravitational processes, not nuclear processes. It's an object in transition, on its way to becoming a star, but not there yet. And all of this is happening in darkness. The protostar glows, yes, but its glow is imprisoned by the cocoon of dust and gas that surrounds it. It shines furiously in the infrared, pouring energy into its envelope, heating the dust around it, driving complex chemistry in the surrounding gas. But none of that light escapes at visible wavelengths. To any observer looking at this region of space with human eyes or an optical telescope, there is nothing to see. Just a dark patch in a dark cloud. The protostar is there. It's real, it's hot, it's luminous, but it's hidden. This hiddenness is not a minor detail. It's central to the entire story of star formation. Stars begin in darkness not just because the raw material happens to be dark, but because the process of building a star requires that darkness. The dust that obscures the protostar is the same dust that helped the molecular cloud cool to the temperatures needed for collapse in the first place. The envelope that hides the protostar is the same envelope that's feeding it, providing the mass that will eventually make it a full-fledged star. The darkness is not separate from the process, it is the process. The obscuration and the formation are the same thing. If you stripped away the envelope, If you somehow removed all the dust and gas surrounding the protostar, you would see a small, hot, glowing object. Reddish in color because its surface temperature is still relatively low compared to a finished star. Larger than the sun in some cases because it hasn't finished contracting yet. Irregular and turbulent because material is still crashing onto its surface from all directions. Not yet spherical, not yet steady, not yet stable. An object in the process of becoming something else. Something that doesn't yet have the internal engine that will eventually define it. Something still wholly dependent on gravity for its warmth and its light. The protostar at this stage is like a furnace that's been lit but hasn't yet caught fire. The heat is there. The glow is there. But the self-sustaining reaction that will keep it burning for billions of years hasn't started. That reaction, hydrogen fusion, requires temperatures that the protostar hasn't reached. Not yet. The core is getting hotter with every passing year as gravity continues to compress it. Every ton of material that falls onto the protostar adds energy. Every increment of contraction raises the core temperature a little more. The protostar is on a slow but inevitable march toward the temperatures and pressures needed to ignite hydrogen fusion. But before it gets there, something else has to happen. Something that will shape not just the protostar itself, but the entire system of planets that might one day surround it. Because the material falling inward doesn't all fall straight down onto the protostar. Something about the physics of the collapse forces the infalling material into a completely different structure. A flat, spinning disk of gas and dust that wraps around the protostar's equator like a cosmic belt. And from the protostar's poles, something even more dramatic erupts. Enormous jets of material blasting outward at hundreds of kilometers per second, punching through the surrounding envelope, carving tunnels through the darkness. These structures, the disk and the jets, are not afterthoughts. They're not minor features. They're fundamental to how a protostar grows, how it regulates its own formation, and how it eventually reveals itself to the universe. The disk is where planets will one day form. The jets are how the protostar expels the excess energy and momentum that would otherwise tear it apart. Together they transform the protostar from a hidden, chaotic, collapsing mess into something approaching order. Something approaching a star. So we left the protostar buried deep inside its natal envelope. Hot, glowing in the infrared, powered entirely by gravity, completely invisible at optical wavelengths. Material is still raining down from the surrounding cloud, adding mass to the protostar with every passing year. But here's something I mentioned briefly a moment ago that we need to explore in detail, because it changes everything about how the protostar grows and eventually reveals itself. Not all of the infalling material falls directly onto the protostar. In fact, most of it can't. And the reason comes down to one of the most fundamental principles in all of physics: conservation of angular momentum. Angular momentum is a measure of how much rotational motion an object has. It depends on the object's mass, how fast it's spinning, and how far the mass is distributed from the axis of rotation. The critical thing about angular momentum is that it's conserved. In any closed system, the total angular momentum cannot change unless an external force acts on it. This is the same principle that makes an ice skater spin faster when she pulls her arms in close to her body. Her angular momentum stays the same, but by pulling her mass closer to her axis of rotation, her rotational speed has to increase to compensate. Nothing was added. Nothing was removed. The angular momentum simply redistributed itself, causing faster rotation as the distribution of mass tightened. Now think about the dense core before it began to collapse. It wasn't perfectly still. Nothing in a molecular cloud is perfectly still. The core had some small amount of rotation. Maybe it was spinning very slowly, barely noticeable. Perhaps it completed one full rotation over the course of 1 million years or more. This tiny bit of rotation seems negligible when the core is enormous, spread across billions of miles. The rotational speed at any given point is minuscule, but as the core collapses, as that vast cloud of gas compresses down toward the center, conservation of angular momentum takes over. Just like the ice skater pulling in her arms, the shrinking cloud spins faster. Material that was barely rotating when it was far from the center is now moving much faster as it falls inward. And this has a profound geometric consequence. Material falling toward the protostar along the poles, along the axis of rotation, doesn't have much angular momentum in the direction that would resist infall. It can fall more or less straight down, but material approaching from the equatorial regions, perpendicular to the rotation axis, has significant angular momentum. As it falls inward and tries to conserve that momentum, it spins faster and faster. At some distance from the protostar, the material is spinning so fast that its centrifugal tendency, the outward push created by circular motion, exactly balances the inward pull of gravity. At that point, the material can't fall any farther inward. It goes into orbit around the protostar instead. This happens to material arriving from all directions around the equatorial plane. It all settles into orbits around the protostar, spreading out into a flat, rotating structure, a disk. This is the accretion disk, sometimes called the protoplanetary disk or protostellar disk. It forms naturally and inevitably from the collapse of any rotating cloud. You don't need special conditions. You don't need unusual physics. As long as the original cloud had even a tiny amount of rotation, and every real cloud does, a disk will form. It's one of the most robust predictions in all of astrophysics, and it's been confirmed by countless observations. The accretion disk is a remarkable structure. It's typically flat, thin relative to its diameter, and roughly circular. In the early stages, when the protostar is still deeply embedded in its envelope, the disk might extend outward for a few hundred astronomical units from the protostar. Remember, 1 astronomical unit is the distance from the Earth to the Sun, so this disk stretches from the protostar outward to a distance several times larger than the orbit of Neptune in our own solar system. The disk is made of the same material as the original cloud, mostly hydrogen and helium gas, with a small fraction of dust grains. But conditions in the disk are very different from conditions in the cold cloud. The inner regions of the disk, closest to the protostar, are hot. Temperatures in the inner disk can reach over 1,000 Kelvin, hot enough to vaporize most solid materials. Farther out, the disk is cooler, dropping to temperatures where water ice and other volatile compounds can exist as solids. This temperature gradient across the disk will eventually have profound consequences for planet formation, but that's a story for another time. The disk is not static. Material within it is constantly moving, spiraling slowly inward toward the protostar. This inward spiral happens because of friction and turbulence within the disk. As particles of gas and dust orbit the protostar, they interact with neighboring particles. These interactions transfer angular momentum outward through the disk. Material that loses angular momentum falls to a tighter orbit, closer to the protostar. Material that gains angular momentum moves to a wider orbit, farther out. The net effect is that most of the mass in the disk gradually spirals inward, feeding the protostar, while a smaller fraction of the mass spreads outward, carrying angular momentum with it. This process is called accretion, and it's how the protostar gains most of its mass during this phase. Material doesn't fall freely from the cloud onto the protostar's surface anymore. Instead, it falls from the cloud onto the outer edge of the disk, and then slowly spirals inward through the disk until it reaches the inner edge, where it finally falls onto the protostar. The disk acts as an intermediary, a transfer station that processes the infalling material and feeds it to the protostar in a controlled way. As material spirals inward through the disk, it releases gravitational energy, heating the disk and contributing to the overall luminosity of the system. The inner regions of the disk glow brightly in the infrared, sometimes rivaling the protostar itself in brightness. The disk is not just a passive bystander, it's an active, dynamic, energy-producing component of the protostellar system. The accretion disk also serves another crucial function. It's the birthplace of planets. The same dust grains that are mixed in with the gas begin to stick together within the disk. Tiny grains collide gently and adhere to each other, forming larger and larger clumps. Over time, these clumps grow into pebbles, then boulders, then objects miles across called planetesimals. Planetesimals collide and merge, building up larger and larger bodies. Eventually, some of these bodies become massive enough for their gravity to attract gas from the surrounding disk, growing into gas giant planets like Jupiter and Saturn. Others remain rocky, like Earth and Mars. This entire process of planet formation happens within the accretion disk, while the protostar is still growing. The protostar and its planets form simultaneously from the same rotating disk of material. This is why our solar system is flat. All the planets orbit the Sun in roughly the same plane, because they all formed from a single flat disk that surrounded the Sun when it was a protostar, 4.5 billion years ago. But the disk isn't the only dramatic structure that forms around the protostar. Something even more violent and spectacular emerges from the protostar's polar regions. Bipolar outflows, enormous jets of material blasting outward from the protostar at incredible speeds, punching through the surrounding envelope and extending for light years into the surrounding interstellar medium. These jets are among the most visually striking phenomena in all of star formation. When astronomers observe star-forming regions with infrared telescopes, they often see long, narrow beams of glowing gas extending outward from deeply embedded protostars. Some jets extend for several light years in opposite directions, creating structures that are far larger than the protostellar system itself. The material in these jets is moving fast. Typical jet velocities range from about 100 to several hundred kilometers per second. Some jets have been measured at speeds approaching 500 kilometers per second. That's over 1 million miles per hour. For context, the speed of sound in air at sea level is only about 1/3 of a kilometer per second. These jets are moving at hundreds of times the speed of sound. How do these jets form? The details are complex and not fully understood even today, but the basic mechanism involves the interaction between the protostar's magnetic field and the accretion disk. Protostars have magnetic fields, inherited from the magnetized gas in the original molecular cloud. As the protostar rotates and the disk orbits around it, these magnetic field lines get twisted and wound up. The twisting magnetic fields act like a spring, storing energy. At some point, the wound-up fields release that energy by launching material outward along the magnetic poles of the protostar. Gas from the inner regions of the accretion disk is funneled along the magnetic field lines, accelerated to high speeds, and ejected in narrow beams perpendicular to the disk. Because the disk is flat and the magnetic poles are perpendicular to the disk, the jets emerge from the top and bottom of the system. Two jets, pointing in opposite directions, forming a bipolar outflow. These jets serve a vital physical purpose. They carry away angular momentum. This is essential for the protostar's survival. Remember, the original cloud was rotating, and as it collapsed, that rotation sped up. The disk formed because the material had too much angular momentum to fall directly onto the protostar. But even the disk can only process so much angular momentum through internal friction. Without another mechanism to remove angular momentum from the system, the protostar would eventually be spinning so fast that centrifugal forces would tear it apart. The jets solve this problem. By flinging material outward at high speeds along the magnetic poles, they carry away enormous amounts of angular momentum. This allows the disk to continue feeding the protostar without the system spinning itself to destruction. The jets are not a side effect of star formation. They're a necessary part of the process. Without them, or something like them, protostars might never be able to accumulate enough mass to become stars. The jets also have a dramatic effect on the surrounding environment. As they slam into the gas and dust of the natal envelope and the surrounding molecular cloud, they create shock waves. These shocks heat and compress the gas, creating bright knots and patches of emission called Herbig-Haro objects, named after astronomers George Herbig and Guillermo Haro, who first studied them in the 1950s. Herbig-Haro objects are visible as small, bright nebulae scattered along the path of the jet. They glow because the shock-heated gas emits light at specific wavelengths, particularly in the lines of hydrogen, oxygen, sulfur, and other elements. Herbig-Haro objects are some of the few visible light signatures of the star formation process. Even though the protostar itself is hidden in darkness, the impact of its jets on the surrounding gas can sometimes be seen with optical telescopes. These glowing patches of shocked gas are like the footprints of an invisible giant, evidence of a hidden protostar's violent activity that can be detected even without infrared instruments. Now, let's talk about what happens to the envelope over time, because this is where the story of the protostar's emergence from darkness begins. The envelope, that thick cocoon of gas and dust that has been hiding the protostar from view, doesn't last forever. It's being attacked from multiple directions simultaneously. From the inside, the protostar's radiation is heating the inner envelope, evaporating dust grains, and pushing gas outward through radiation pressure. The jets are carving cavities through the envelope, punching holes that allow some of the protostar's light to escape along the jet axis. And the accretion process itself is consuming the envelope. Material that falls onto the disk and then spirals onto the protostar is material that's been removed from the envelope. With every passing year, the envelope gets a little thinner, a little less opaque, a little less effective at hiding the protostar within. This process of envelope dispersal happens over hundreds of thousands of years. It doesn't happen all at once. The envelope doesn't suddenly vanish. It thins gradually like fog burning off in the morning sun. At first, the only openings are the narrow cavities carved by the jets. Some infrared light from the protostar and the inner disk escapes through these cavities, creating bright infrared nebulae visible along the jet axis. As the envelope continues to thin, more and more light escapes. The protostar becomes progressively more visible at shorter and shorter wavelengths. First in the far infrared, then in the mid-infrared, then in the near-infrared, and eventually, as the last wisps of envelope are blown away or accreted, invisible light. Astronomers have organized this progression into a classification system based on how the protostellar system's spectrum looks at infrared wavelengths. The system divides protostars into classes numbered from 0 to 3, roughly corresponding to evolutionary stages. A class 0 protostar is the youngest and most deeply embedded. It's still surrounded by a massive envelope, accreting material rapidly. Most of its luminosity comes out at far infrared and submillimeter wavelengths, because the dust is so thick that even mid-infrared radiation can barely escape. Class 0 protostars are almost completely invisible at near-infrared and visible wavelengths. They are the most hidden, the most obscured, the deepest in darkness. They typically represent the first few tens of thousands of years after the protostellar core forms. A Class 1 protostar is slightly more evolved. The envelope has thinned somewhat. The jets have carved significant cavities. Mid-infrared radiation can now escape more freely, and the protostar might even be detectable at near-infrared wavelengths, though still heavily obscured. The accretion disk is well established, and accretion is still ongoing, though possibly at a slower rate than during the Class 0 phase. Class 1 protostars represent a phase lasting roughly 100,000 to 200,000 years after formation. By Class 2, the envelope has largely dispersed. The protostar is now visible at near-infrared and even optical wavelengths. The accretion disk is still present, but is no longer being fed by a significant infalling envelope. At this point, the object is often called a T Tauri star if it's a low-mass protostar, named after T Tauri, a young star in the constellation Taurus that was the prototype for this class of objects. T Tauri stars are visible to optical telescopes. They look like stars, but they're not yet on the main sequence. They're still contracting, still deriving much of their energy from gravity rather than fusion. They often show signs of residual accretion, with gas from the disk still falling onto the stellar surface. They exhibit strong magnetic activity, producing intense flares and energetic outbursts. They are stars in the process of finishing their formation, still settling into the stable configurations they will maintain for billions of years. Class 3 objects have lost most or all of their disk material. The accretion has ceased. The object is now a pre-main sequence star, contracting slowly toward the main sequence. It might still be slightly larger and more luminous than it will be as a finished star, but it's recognizably star-like. The darkness that once hid it is gone. The envelope has been dispersed. The disk is either gone or reduced to a thin remnant. The object is now a naked young star, exposed to the universe, shining in visible light for the first time. This classification system, from Class 0 through Class 3, is essentially a timeline of how a protostar reveals itself. It goes from completely hidden, buried in a dense envelope of gas and dust, invisible at all wavelengths shorter than the far infrared, to fully revealed, standing alone as a young star visible in optical light with no remaining envelope. The journey from darkness to light takes a few 100,000 to a few million years, depending on the mass of the protostar and the conditions in its environment. The tools we use to observe each stage are different precisely because of how the envelope controls what wavelengths of light can escape. To study Class 0 protostars, the youngest and most deeply embedded, we need far infrared and submillimeter telescopes. The Herschel Space Observatory was ideal for this, operating at wavelengths between 70 and 500 micrometers. ALMA, which operates at millimeter and submillimeter wavelengths, can image the structure of Class 0 protostellar systems in extraordinary detail, resolving the disk, the envelope, and even the outflow cavities. For Class 1 protostars, mid-infrared instruments become useful. The Spitzer Space Telescope observed thousands of Class 1 objects across the Milky Way. The James Webb Space Telescope, which operates at near and mid-infrared wavelengths with unprecedented sensitivity and resolution, is now revolutionizing our understanding of these intermediate stage protostars. Webb can peer through the residual dust that still partially obscures Class 1 and young Class 2 objects, and reveal the structures within, the disks, the jets, the inner envelopes, with a clarity that was previously impossible. For Class 2 and Class 3 objects, the T Tauri stars, and their slightly more evolved successors, even optical telescopes can contribute. These objects are visible in the same kind of light our eyes detect. Ground-based optical telescopes and space-based instruments like the Hubble Space Telescope have studied thousands of T Tauri stars, revealing their disks, their magnetic activity, their flares, and their interactions with their environments. Hubble has taken stunning images of protoplanetary disks seen edge-on, appearing as dark silhouettes against the bright background of star-forming nebulae. These images show the disks as thin, flat structures, exactly as predicted by theory, confirming that the conservation of angular momentum does indeed produce the flattened structures we expect. One of the most spectacular star-forming regions visible from Earth is the Orion Nebula, located about 1,344 light-years away in the constellation Orion. The Orion Nebula is a giant cloud of gas and dust that's actively forming stars right now. Within it, astronomers have identified hundreds of young stellar objects in various stages of formation. Some are still deeply embedded Class 0 or Class 1 protostars, detectable only at infrared and submillimeter wavelengths. Others are Class 2 T Tauri stars with prominent accretion disks. Still, others are more evolved, nearly finished with their formation process. The Orion Nebula is like a laboratory of star formation, containing examples of virtually every stage of the process, all in one relatively compact region of space. Within the Orion Nebula, the Hubble Space Telescope discovered what astronomers call proplids, short for protoplanetary disks. These are accretion disks around young stars that are visible because they're being illuminated and evaporated by the intense ultraviolet radiation from nearby massive stars. The proplids appear as small, tadpole-shaped objects, each containing a young star surrounded by a disk of gas and dust. The ultraviolet radiation from the massive stars is slowly destroying these disks, stripping away gas from their outer edges. This means the planets forming within these disks have a limited time window. If the disk is destroyed before planets have finished forming, the process stops. This is a reminder that star formation doesn't happen in isolation. Young protostars and their disks are often influenced by the massive stars forming nearby, and this can either help or hinder the planet formation process. ALMA has provided some of the most detailed images of accretion disks ever obtained. In 2014, ALMA released an image of the disk around T Tauri, a young star about 450 light-years away. The image showed a series of concentric bright and dark rings in the disk, like the grooves on a vinyl record. The dark rings are gaps in the disk, where material has been cleared away, possibly by forming planets sweeping up dust and gas along their orbits. This image was a revelation. It showed that planet formation might begin even earlier than previously thought, while the star is still very young and still accreting material from its disk. The disk around T Tauri is probably less than 1 million years old, and already the patterns of planet formation appear to be visible. These observations have transformed our understanding of how stars form. 50 years ago, star formation was largely theoretical. We could see the end products, the finished stars, and we could see the raw material, the molecular clouds. But the process connecting the two was hidden in darkness, inaccessible to our instruments. Today, thanks to infrared, submillimeter, and millimeter wave astronomy, we can observe every stage. We can watch as dense cores collapse. We can detect the first warm glow of a newborn protostar buried in its envelope. We can image the accretion disks and jets. We can follow the gradual dispersal of the envelope and the emergence of the young star into visible light. We can see planets beginning to form in the disk, while the star itself is still under construction. Each technological advance has peeled back another layer of darkness, revealing more of the hidden process within. And yet, there are still mysteries. We don't fully understand how the magnetic fields interact with the disk to launch jets. We don't know exactly how angular momentum is transported through the disk. We aren't certain about the details of how the first planetesimals form from tiny dust grains. Each answered question reveals new questions beneath it. But the broad picture is now clear. A protostar forms in darkness, surrounded by an envelope, fed by a disk, sculpted by jets. Over hundreds of thousands of years, the envelope disperses, the darkness lifts, and the object that was hidden for so long, that glowed unseen in the infrared, that grew quietly in the cold heart of a molecular cloud, finally stands exposed. But it's still not a true star. Not yet. The darkness is gone, the envelope is gone, the disk may be fading. But deep inside the protostar's core, the temperature still hasn't reached the critical threshold. Hydrogen fusion hasn't ignited in a sustained way. The protostar is still powered by gravity, still contracting, still heating up. It has come an extraordinary distance from the cold, dark knot of gas where it began. It's gone from 10 Kelvin to millions of degrees at its core. It's gone from invisible to luminous. It's gone from a diffuse cloud hundreds of billions of miles across to a coherent, hot, glowing object a few times the size of the sun. But the final step, the step that will transform it from a protostar into a star, is still ahead. The core must get hotter still. The contraction must continue, and somewhere in the deep interior, at temperatures and pressures that would obliterate any material on Earth, hydrogen nuclei must begin to merge. That moment, the ignition of sustained hydrogen fusion, is the true birth of a star, and reaching it requires one last transformation. So the envelope is gone. The thick cocoon of gas and dust that hid the protostar for hundreds of thousands of years has been dispersed, blown away by outflows, consumed by accretion, eroded by radiation. The protostar is now exposed. For the first time in its existence, it's visible at optical wavelengths. If you pointed a telescope at it, you would see a glowing object, reddish or orange in color, larger than our sun, brighter than you might expect for its temperature, because its bloated size compensates for its relatively cool surface. It looks like a star. It's in the sky where stars are. It glows like a star. But it's not a star. Not yet. What you're looking at, if this is a low-mass object forming along a path similar to how our own sun formed, is a T Tauri star, named after the prototype object T Tauri, discovered in the constellation Taurus. These are young stellar objects that have emerged from their natal envelopes, but haven't yet ignited sustained hydrogen fusion in their cores. They're pre-main sequence objects. The term main sequence refers to the stable phase of a star's life, when hydrogen fusion in the core produces enough energy to balance gravity. A main sequence star is in equilibrium. Energy produced by fusion flows outward, creating pressure that supports the star against gravitational collapse. This balance can persist for millions, billions, or even trillions of years depending on the star's mass. A T Tauri star hasn't reached that balance yet. It's still on its way there. T Tauri stars are fascinating objects in their own right. They're among the most active and variable young stars we can observe. They exhibit dramatic changes in brightness over timescales of days to weeks, sometimes brightening or dimming by a factor of 2 or more. Some of this variability comes from residual accretion. Even though the massive envelope is gone, the accretion disk often persists for several million years after the envelope disperses. Gas from the inner edge of the disk still trickles onto the stellar surface, channeled by magnetic field lines. When this gas, moving at speeds of hundreds of kilometers per second, hits the stellar surface, it creates hotspots, bright, localized regions that can significantly affect the star's overall brightness. As the star rotates, these hotspots come in and out of view, causing the observed brightness to vary periodically. T Tauri stars also exhibit powerful magnetic activity. Their magnetic fields are much stronger than the sun's current field, often hundreds or thousands of times stronger. These intense fields drive energetic flares, sudden releases of magnetic energy that can temporarily increase the star's brightness by enormous amounts, particularly at X-ray and ultraviolet wavelengths. Some T Tauri flares release more energy in minutes than our sun releases in hours. The magnetic fields also interact with the disk, creating complex structures where gas flows along field lines from the disk to the star. This magnetospheric accretion is a defining characteristic of the T Tauri phase. It creates a dynamic, turbulent interface between the star and its disk that's unlike anything seen in mature stars. T Tauri stars are also often associated with dramatic outflow activity. While the massive bipolar jets of the deeply embedded protostellar phase may have weakened, many T Tauri stars still drive outflows and winds. These winds are slower and less collimated than the earlier jets, but they're still significant. They help clear away the remaining disk material and contribute to the overall dispersal of the birth environment. Some T Tauri stars also drive what are called Fu Orionis outbursts, named after the star Fu Orionis. These are episodes of dramatically increased accretion, where the rate of material falling from the disk onto the star suddenly jumps by a factor of 100 or more. During an Fu Orionis outburst, the star can brighten by a factor of 100 or more in visible light, sometimes over the course of just months or years. The outbursts can last for decades or even centuries before fading. These events are thought to be caused by instabilities in the accretion disk that suddenly dump large amounts of material onto the star. They remind us that even at this relatively advanced stage, star formation is not a smooth, steady process. It is punctuated by violent episodes of rapid change. For intermediate mass protostars, those between roughly 2 and 8 times the mass of the Sun, the equivalent pre-main sequence objects are called Herbig A, B stars, named after George Herbig, who first identified them as a distinct class. These objects are hotter and more luminous than T Tauri stars. They're also rarer because intermediate mass stars are less common than low mass stars. Herbig A, B stars still have accretion disks and still show signs of youth, but their higher luminosities and temperatures mean they evolve faster toward the main sequence. Their disks tend to disperse more quickly, partly because the more intense radiation from the central star erodes the disk material more rapidly. For the most massive protostars, those destined to become stars 10 or 20 or 50 or even 100 times the mass of the Sun, the pre-main sequence phase is fundamentally different. These objects form so quickly and generate so much energy that they can ignite hydrogen fusion in their cores while still accreting material through a disk, and while still partially embedded in remnant envelope material. A massive protostar doesn't wait politely for its envelope to clear before becoming a star. It powers through. The enormous luminosity of a massive protostar, sometimes tens of thousands or hundreds of thousands of times the luminosity of the Sun, generates fierce radiation pressure that actively blows away the surrounding material. Massive stars fight their way out of their birth clouds by sheer brute force. They're also much harder to observe during formation because they're rarer. They form in more distant and crowded regions, and they evolve so quickly that catching one in the act of formation is statistically difficult. Much of what we know about massive star formation is still being refined as new observations from ALMA and the James Webb Space Telescope provide unprecedented views of these energetic systems. But let's return to the more common low-mass case and follow the protostar through its final transformation. Because whether the star is low mass or high mass, the fundamental question is the same. What has to happen for a protostar to become a true star? The answer is deceptively simple. The core temperature must reach approximately 10 million Kelvin. At 10 million Kelvin, hydrogen nuclei begin to fuse through a process called the proton-proton chain. This is the dominant fusion process in stars like our Sun and in stars smaller than about 1.3 solar masses. Here's how it works. A hydrogen nucleus is just a single proton. At the temperatures and pressures inside a stellar core, protons are moving incredibly fast, slamming into each other with enormous force, but protons are positively charged, and like charges repel. Two protons rushing toward each other feel an increasingly powerful electrostatic repulsion as they get closer. At everyday temperatures, this repulsion would prevent them from ever touching. They'd bounce off each other like two magnets held with the same poles facing. But at 10 million Kelvin, the protons are moving so fast that they can overcome this repulsion and get close enough for a different force to take over. The strong nuclear force. This force operates only at extremely short range, less than a femtometer, which is 1/quadrillionth of a meter. But within that range, it's enormously powerful, far stronger than the electromagnetic repulsion. When two protons get close enough for the strong force to grab them, they can fuse together. One of the protons converts into a neutron through a process involving the weak nuclear force, releasing a positron and a neutrino. The result is a deuterium nucleus, one proton and one neutron bound together. This is the first step of the proton-proton chain. The deuterium nucleus then quickly fuses with another proton to form helium-3, a nucleus with two protons and one neutron. This reaction also releases a gamma-ray photon, a high-energy particle of light. Finally, two helium-3 nuclei collide and fuse to form helium-4, a nucleus with 2 protons and 2 neutrons, releasing 2 protons back into the gas in the process. The net result of this chain of reactions is that 4 hydrogen nuclei have been combined into one helium-4 nucleus, but the helium-4 nucleus has slightly less mass than the 4 original hydrogen nuclei combined. About 0.7% of the mass is missing. Where did it go? It was converted into energy according to Einstein's famous equation E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is an enormous number, and when you square it, it becomes truly staggering. Even a tiny amount of mass converts into an enormous amount of energy. That 0.7% might not sound like much, but when you're converting millions of tons of hydrogen into helium every single second, the energy output is colossal. Our sun converts about 600 million tons of hydrogen into helium every second. In doing so, it loses about 4 million tons of mass every second. Mass that's converted directly into energy. This is the energy that lights the sun. This is the energy that heats our planet. This is the energy that makes life on Earth possible. But for a protostar, this process hasn't started yet. The core isn't hot enough. 10 million Kelvin is the threshold, and the protostar's core is still below that mark. So how does the core temperature continue to rise? The same way it's been rising since the collapse began. Gravity. The protostar is still slowly contracting. Without a sustained internal energy source to fully balance gravity, the star continues to shrink. As it contracts, the core gets compressed further, and compression raises temperature. This is the Kelvin-Helmholtz contraction I described earlier, operating on a timescale of millions of years. The protostar is slowly, steadily converting gravitational potential energy into thermal energy, inching its core temperature higher and higher. The rate of this contraction depends on the mass of the protostar. More massive protostars contract faster and reach the fusion threshold sooner. A protostar with 10 times the mass of the Sun might reach the main sequence in less than 100,000 years. The contraction is so fast that such a star is still embedded in its birth material when fusion ignites. A protostar with a mass similar to our Sun takes roughly 10 to 50 million years to reach the main sequence. The contraction is slower, more gradual. The envelope has long since dispersed. The accretion disk may have faded or disappeared entirely by the time the core finally reaches 10 million Kelvin. For the very lowest mass protostars, those with less than about half the mass of the Sun, the journey to the main sequence can take hundreds of millions of years. These objects contract so slowly and their cores heat so gradually that they spend an extraordinarily long time as pre-main sequence objects before fusion finally begins. And there's a category of objects that never make it at all. These are brown dwarfs, sometimes called failed stars. A brown dwarf forms in exactly the same way as a normal protostar. It begins as a dense core in a molecular cloud. It collapses under gravity. It heats up through compression. It develops a disk and possibly drives outflows. It emerges from its envelope as a warm, glowing, contracting object. It looks like a protostar. It acts like a protostar. But it doesn't have enough mass. The threshold for sustained hydrogen fusion is roughly 80 times the mass of Jupiter, or about 8% of the mass of the Sun. If the object's total mass falls below this threshold, the core simply never gets hot enough. It contracts and contracts, its core temperature climbing higher and higher, approaching but never reaching the critical 10 million Kelvin needed for the proton-proton chain. The core might reach a few million Kelvin. It might fuse deuterium for a while, since deuterium fusion requires lower temperatures, but the ordinary hydrogen, the fuel that would power a true star for billions of years, never ignites. Without that sustained energy source, the object has nothing to balance gravity in the long term. It continues to contract very slowly and cool off over billions of years, radiating away the heat generated by its formation and initial contraction. It's a warm object at first, glowing dimly in the infrared, but it fades and cools over time. It never becomes a true star. It never joins the main sequence. Brown dwarfs occupy a strange middle ground between giant planets and small stars. They're more massive than any planet in our solar system, but less massive than the smallest true stars. They glow, at least initially, powered by residual heat from their formation and by brief episodes of deuterium fusion. But they lack the defining characteristic of a star. They lack sustained hydrogen fusion. They went through the entire process of protostellar formation, the collapse, the heating, the disk, the outflows, the envelope dispersal, everything. And at the end of it all, they fell just short. Not enough mass, not enough compression, not enough heat. The universe set a threshold, and they didn't cross it. Brown dwarfs are a reminder that the journey from cold gas to shining star is not guaranteed. The process can begin and still fail. Not every collapsing core produces a star. Some produce something that almost becomes a star but doesn't quite make it. Doomed to slowly cool in the darkness for the rest of time. This relationship between mass and formation time is one of the most important patterns in stellar astrophysics. Massive stars form fast, live fast, and die fast. Low-mass stars form slowly, live slowly, and persist for immense stretches of time. Our Sun took, perhaps, 30 to 50 million years from the initial collapse of the dense core to the ignition of sustained hydrogen fusion. In cosmic terms, that's relatively quick. But in human terms, it's an eternity. 50 million years ago, dinosaurs had already been extinct for 16 million years. Early primates were just beginning to appear. The continents were in different positions. The world was unrecognizable. The formation of a star like our sun spans timescales that dwarf everything in human experience. Now, let's witness the actual moment. After millions of years of slow contraction, the core temperature of the protostar finally approaches 10 million Kelvin. Hydrogen nuclei in the core are now moving at tremendous speeds, colliding with incredible force. The first fusion reactions begin to occur, not all at once, not in a sudden explosion. The process starts gradually. A few protons fuse, then a few more. Each reaction releases a small amount of energy. That energy heats the surrounding gas slightly, which increases the reaction rate slightly, which releases slightly more energy. It's a positive feedback loop, but it's regulated by the physics of the situation. If the core gets too hot, it expands slightly, which reduces the density and temperature, which slows the reaction rate. If the core cools, it contracts, which increases the density and temperature, which speeds up the reactions. This self-regulating mechanism is what makes main sequence stars so stable. The fusion reactions act like a thermostat, automatically adjusting to maintain equilibrium. Over a relatively short period, the fusion reactions ramp up until they're producing enough energy to fully balance gravity. The contraction stops. The star reaches hydrostatic equilibrium. Energy produced by fusion in the core flows outward through the star, first by radiation, then by convection in the outer layers, and finally escapes from the surface as the light and heat we observe. The star has arrived on the main sequence. It is now, for the first time in its existence, a true star. This moment, the arrival on the main sequence, is quiet. There's no explosion, no flash of light visible from the outside that would announce the event. The star was already glowing before fusion began, powered by gravitational contraction. The transition to fusion power is seamless from an external perspective. The star simply stops contracting. Its luminosity stabilizes. Its surface temperature settles to a value determined by its mass. It begins the long, stable phase of its life that will last for millions or billions of years. From the outside, nothing dramatic appears to happen. The drama was all internal. Deep in the core, at temperatures and pressures that would obliterate anything on Earth, protons began to merge. And in that merging, a star was truly born. For a star like our Sun, the main sequence lifetime is about 10 billion years. Our sun is currently about 4.6 billion years old, roughly middle-aged. It will continue burning hydrogen in its core for another 5 billion years or so, before it exhausts its fuel and begins to die, swelling into a red giant and eventually shedding its outer layers to leave behind a white dwarf. But for now, it burns steadily, stably, the product of a process that began in absolute darkness inside a molecular cloud roughly 4.5 billion years ago. Let's step back for a moment and consider the full timeline. From the beginning of collapse to the arrival on the main sequence, what has actually happened? A dense core of gas and dust, perhaps a few tenths of a light year across, sitting in the dark interior of a giant molecular cloud at a temperature of about 10 Kelvin, lost its battle against gravity and began to collapse. The collapse concentrated the material at the center, forming a small, hot, dense object. The protostellar core, powered entirely by gravitational energy. An accretion disk formed around this object, feeding it material. Jets erupted from its poles, carrying away angular momentum. The surrounding envelope was gradually consumed and dispersed over hundreds of thousands of years. The object emerged from its cocoon as a T Tauri star, visible for the first time in optical light. It continued to contract for millions of years, its core temperature climbing steadily. And finally, when the core reached approximately 10 million Kelvin, hydrogen fusion ignited, the contraction halted, and the object became a main sequence star. The entire process, from initial collapse to main sequence arrival, took somewhere between 10 million and 50 million years for a star like the Sun. For massive stars, it can be as short as 100,000 years. For the lowest mass stars, it can stretch to hundreds of millions of years. But regardless of mass, the fundamental story is the same. Darkness first, then gravity, then heat, then light, then fusion, then a star. And here's what's truly remarkable when you step back and think about it. Every star you have ever seen in the night sky went through this process. Every single one. Sirius, the brightest star in the night sky, 8.6 light years away. It began as a cold, dark knot of gas in a molecular cloud millions of years ago. Betelgeuse, the red supergiant in Orion, roughly 650 light years away. It was once a protostar buried in darkness, invisible to any optical telescope. Polaris, the North Star, Vega, Rigel, Aldebaran, the stars of the Southern Cross. Every star in every constellation in every culture's mythology. All of them were born in darkness. All of them began as collapsing clouds of cold gas and dust. All of them spent hundreds of thousands of years hidden inside cocoons of opaque material, growing in secret, warming in silence. All of them emerged from that darkness only after the patient work of gravity had compressed and heated them enough to become visible. And all of them eventually crossed the threshold into sustained hydrogen fusion, becoming the brilliant, stable, shining objects we see when we look up at night. Our own sun went through this exact process 4.5 billion years ago. The molecular cloud that gave birth to the sun probably also gave birth to hundreds or thousands of other stars, sibling stars that have long since drifted away from each other, scattered across the galaxy by billions of years of orbital motion. Those sibling stars are out there somewhere in the Milky Way, shining steadily, each one unaware of its connection to our sun, each one born from the same cloud, the same darkness, the same ancient collapse. The atoms in your body, the carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was present in that original cloud. Some of those atoms were forged in even older stars that lived and died before our sun was born, their ashes enriching the molecular cloud with the heavy elements needed to build rocky planets and living organisms. You are, in the most literal and physical sense, a product of the same process that turned cold darkness into starlight. There's something deeply moving about this. The brightest objects in the universe begin in the darkest places. Light comes from darkness. Stars are born hidden, invisible, buried in cocoons of dust that block every photon of visible light. For hundreds of thousands of years, a forming star is the universe's best-kept secret, growing in silence, unseen by any eye, unknown to any observer unless they happen to have the right instruments, tuned to the right wavelengths. And then, slowly, gradually, the darkness lifts. The envelope thins, the dust clears, and what was hidden is revealed. A new star, glowing, hot, fusing hydrogen in its core, contributing its light to the great tapestry of the night sky. A light that may shine for billions of years. A light that may warm planets. A light that may, in at least one case that we know of, make life possible. The universe is filled with molecular clouds right now. The Milky Way alone contains thousands of giant molecular clouds, each one containing enough material to form thousands of stars. Inside those clouds, right now at this very moment, dense cores are collapsing. Protostars are forming. Accretion disks are spinning. Jets are blasting through envelopes. Stars are being born in darkness, just as they've been born for the last 13 billion years, since the first molecular clouds formed in the first galaxies. Star formation is not a historical event that happened once and stopped. It's an ongoing process. It's happening right now. Somewhere in the Milky Way, at this very instant, a dense core is crossing the threshold from stability into collapse. Gravity is taking hold. Cold gas is beginning to fall inward. And something that will eventually shine for billions of years is starting its long journey from darkness into light. You can't see it. Not with your eyes. Not with an optical telescope. It's hidden, buried deep inside a cloud of dust in some distant corner of the galaxy. But it's there. And if you had the right instruments, a far infrared telescope or a submillimeter array, you could detect the faint warm glow of its earliest moments. The first tentative heat of gravitational compression. The first infrared whisper of a protostar just beginning its existence. And billions of years from now, long after our sun has died and faded to a cold white dwarf, that protostar will still be shining. It might be a small red dwarf, burning its fuel so slowly that it will outlast nearly everything else in the galaxy. It might warm planets of its own. Life might arise on one of those planets. Beings might look up at their night sky and see the distant stars and wonder where they came from. And the answer will be the same answer we've discovered here tonight. Stars come from darkness. They are born in the coldest, darkest, most hidden places in the galaxy. They begin as nothing more than cold gas responding to gravity. And through a process that spans millions of years, through collapse and compression and heating and accretion and outflow and the slow dispersal of obscuring dust, they transform from invisible knots of frigid gas into the brilliant, blazing, magnificent objects that light up the cosmos. Every point of light in the night sky is a triumph over darkness. Every star is a testament to what gravity can build from almost nothing. And every time you look up and see the stars, you're seeing the end result of a process that began in places so dark and so cold that they represent the most extreme environments in the galaxy. The universe builds its brightest creations from its darkest raw materials. And that, perhaps, is one of the most beautiful truths in all of nature. A star begins in darkness. It earns its light through millions of years of patient gravitational work. And when it finally shines, it shines with a brilliance that can last for billions of years, from cold and dark to hot and bright, from hidden to revealed, from silence to radiance. That is what a protostar really is. And that is why a star begins in darkness. The next time you stand outside on a clear night and look up at the sky, pick any star, any point of light at all, and remember that it was once invisible. It was once a cold knot of gas sitting in the dark interior of a cloud, with no light, no heat, no hint of what it would become. It sat in that darkness for perhaps 1,000,000 years, before something tipped the balance and gravity took hold. It fell inward for hundreds of thousands of years, hidden from view, slowly warming through nothing but compression. It built a disk around itself, launched jets from its poles, cleared away the dust that concealed it, and slowly, over millions of years, contracted and heated until deep in its core, hydrogen nuclei began to fuse. And in that moment, it became what you see tonight. A star, burning steadily, shining across the light years, a beacon of light born from absolute darkness. That journey from cold gas to stellar fire is one of the most extraordinary transformations in all of nature, and it happens somewhere in this galaxy every single day. The darkness is always producing new light. That is how the universe works. That is how it has always worked. And that is how it will work for trillions of years to come, long after every star you can see tonight has burned out and faded. New ones will rise from the dark. They always do.